Good morning, class. We are looking at Chapter 3, Derivatives, Section 3.3, Basic Differentiation Formulas. Chapter 3, Derivatives, we looked at derivatives and rates of change, the derivatives as a function, and now basic differentiation formulas. The formulas we are looking at mainly in this section are as follows. d dx, the derivative of c is 0. C is a number, is a constant. d dx of x to the power of n is n x to the power of n minus 1. This is called the power rule. d dx of e to the power of x, the derivative of e to the power of x is itself. The derivative of sine is cosine. The derivative of cosine is negative sine. Now again, I want you to look at all these expressions, including this pair, reminding you of rise over run. You're given 2 points. You're calculating this slope. Delta y over delta x in various formats. In this graph, as q approaches p, gives rise to the line, the red line known as the tangent line. The tangent line is the limiting position of a secant line PQ as Q approaches P. Slope of a tangent line, or the instantaneous rate of change at a specific point, limit of f of x minus f of a over x minus a as x approaches a, or the limit of f of a plus h minus f of a over h as h approaches 0. And using point slope form on the pair a comma f of a, you come up with the equation of a tangent line at the pair y minus f of a equals f prime of a times x minus a. However, just you don't have to memorize that. Follow the point slope. And in general, instead of saying a and f of a, it's x and f of x, and this is x plus h, f of x plus h, we have f prime of x. Definition, limit of f of x plus h minus f of x over h as h approaches 0. So that's what we've looked at. And now the basic differentiation formulas. When f of x is a c, a constant, a number, its derivative is 0. And here's the justification. If you go with the graph, the line y equals c is a horizontal line, and any horizontal line, the slope is 0. So f of x equals c, or y equals c, f prime becomes 0 because any horizontal line has a slope which is 0. If we go with the definition, limit of f of x plus h minus f of x over h as h approaches 0. The limit as h approaches 0, fraction bar h. What is f of x plus h? Because c is a constant, it's independent of x. F of x plus h, or f of any number, is still the same thing, c. So c minus c, which becomes 0 over h. 0 over h is 0, and therefore the limit is 0. So that's a proof using the definition. That's a proof using lines. So in short, derivative of a constant function, d dx of c, is equal to 0. Reminding you of compound interest, a equals p times 1 plus r over n to the power of nt, where p is the principal, r is the rate, n is the number of compounding per year, t is the number of years, a is the amount we end up with. If we choose r over n to be 1 over m, if we choose that, then the reciprocal of this m is n over r. And if you look at the cross product, n is r times m. So here's what we are going to do. We're going to change r over n to 1 over m. And we're going to change n r times m, or m times r. And when we look at this format, this portion, as you recall, in the case of a compound interest continuously, a equals pe to the power of rt, means this part is e, and therefore e has this definition: limit as m approaches infinity of 1 plus 1 over m to the power of n. Now let's play with 1 over m and call it h. If we call it h, m is 1 over h, which means h and m are two numbers that are reciprocal of each other. So because m is approaching infinity, h must approach 0. So we're going to change this in the following manner. We're going to write limit of 1 plus 1 over m, we're going to call it h. M becomes 1 over h. And if m approaches infinity, h approaches 0. So we're going to write another definition for E, the limit of 1 plus h to the power of 1 over h as h approaches 0. And as you know, E is a number, is an irrational number 2.71828, and it continues indefinitely. Now, I'm going to change the m to n on purpose. I want to make sure you understand that this, if m, those three are the same, n, or x or y, or any variable of your choice, that means the same thing. The same as far as h is concerned, the same thing. We're going to change it to x. So x, 1 over x, x approaching 0. So the reason I mentioned it depends on the text. You may encounter this formula, which means this one, or this formula, which means this. And finally, the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. We are going to look at that one in this course. So now, differentiation formulas, we are going to look at the power rule. The derivative of x to the power of n is nx to the power of n minus 1. And according to the power rule, if you choose it to be x, the derivative of x with the power rule becomes 1, because the exponent is 1. So 1 sits in front. X to the power of 1 minus 1 is 0. X to the power of 0 is 1. So the answer is 1. The constant multiple. If c is a constant and f is a differentiable function, d dx of c f of x is c d dx of f of x, meaning the constant comes out. The following rules, including this one, really follow limit laws, the sum rule. If f and g are both differentiable functions, then d dx of f of x plus g of x is d dx of f of x plus d dx of g of x, which means the derivative of the sum is the sum of the derivatives. The difference rule, the derivative of the difference is the difference of the derivatives. And so here's the basic formulas that we want to discuss. First and foremost, we looked at those. And we will look at those later on, the derivative. We're going to add those. The derivative of tangent is secant squared, cotangent is negative cosecant squared, secant is secant x tan, and the derivative of cosecant is negative cosecant x, cotangent x. For now, those are the ones that we are going to look at. So I want to start with the proof for the power rule. You're not responsible for the proof, but if you can follow it, you're in good shape as far as the definition is concerned. When f of x is x to the power of n, we want to prove the derivative is in x to the power of n minus 1, and we're going to go with f prime of x is limit of f of x plus h minus f of x over h as h approaches 0. So what is this equal to? F of x plus h is x to the power of n plus h. The rest of them just simply themselves. Meaning f of x is x to the power of n and h is a. So we want to expand that. To expand that, I want to remind you of a couple of things. One of them is a factorial. Recall, n factorial means n times n minus 1 times n minus 2 all the way to 1. So 0 factorial, like 1 factorial equals 1, and 0 factorial is equal to 1 because of the combination problem. As an example, 5 factorial means 5 times 4 times 3 times 2 times 1, which adds up to 120 when you multiply them up. Binomial theorem, what was it in algebra? A plus b to the power of n is combination of n choose 0, a to the power of n, b to the power of 0, combination of n choose 1, a to the power of n minus 1, b to the power of 1, and you finish it with combination of n choose n, a to the power of 0, b to the power of n. A couple of them that we have seen, those identities, for example, a plus b squared is really from binomial theorem, which is a squared plus 2ab plus b squared. A plus b cubed, the same thing, a cubed plus 3a squared, b plus 3ab squared plus b cubed. We've seen that one also. And the combination has the formula combination of n choose r is n factorial over r factorial times n minus r factorial. This is one way to write it. You might write CNR. So if that is the case, n choose 0 and n choose n, both of them are 1. Okay, I show you one of them. For example, n choose 0 according to this formula becomes n factorial over 0 factorial, n minus 0 factorial. As you can see, this is 1. This is n factorial, that becomes 1. So believe it or not, this is 1, and I'm going to leave it for you to prove this one is 1. And this one, n choose 1, is equal to n. Let's look at it. According to this formula, becomes n factorial over 1 factorial times n minus 1 factorial. We should know that this can be replaced by n times n minus 1 factorial. These two cancel each other, and we get n. That's how we arrive at the answer. Now, why are we writing those? Let's find out. So, to expand this, according to this one becomes n0, which is 1, a to the power of n, which is x to the power of n, b to the power of 0, which means h to the power of 0, which is 1. So simply put, this one says this is x to the power of n. This one is n, x to the power of n minus 1. B to the power of 1 means h to the power of 1, or simply h. And you continue all the way to the last one, which x to the power of n becomes h to the power of n. So this is n, and you write it. So when you expand this, this is what you get. Now notice, I write the first one as x to the power of n, the second one as n x to the power of n minus 1h, because the exponents, everybody, they must add up to n. Look at all of them, okay? Now this one, I keep it just the way it is. N choose 2, a to the power of n minus 2, in this case, x to the power of n minus 2, b squared becomes h squared. We continue, the last one is h to the power of n, and the one before that, nx h to the power of n minus 1. Clearly, these two cancel each other. Clearly, we can take the h out. If I take the h out from what is left, this one doesn't have a h. This one takes h to the power of 1. This one h to the power of n minus 2, and this one h to the power of n minus 1. Cancel out the h from the top and the bottom. And what you're left with, if you look at this expression, every expression involves h except the first one. Because h approaches 0, every expression, every term goes to 0 except the first one. And we just proved when f of x is x to the power of n, f prime is n, x to the power of n minus 1. As I've mentioned, this is, you're not responsible for the proof, but if you follow it, it makes it easy to understand the definition. All right, now let's differentiate, and we are looking at the power rule. This one, 6 sits in front, x to the power of 6 minus 1, 6x to the power of 5. This one, y equals x to the power of 1000. Put the 1000 in front, x to the power of 1000 minus 1, or 999. Same thing here, put the 4 in front, t cubed. Now, the reason I'm writing this format also, just to emphasize, Leibniz's notation will make sure we understand the independent variable, and the independent variable is t. What about these two functions? First and foremost, this one, everybody, if I want to differentiate, y prime becomes 3, and then 2r to the power of 2 minus 1, and we get 6r. So the answer is 6r. What I want to emphasize, In Leibniz's notation, you could write dy dr, or you can write d dr of 3r squared. And again, we are emphasizing the independent variable is r. In this case, you multiply the 6 by 10, you get 60, and 6 goes down to 5. So we are using the simple case of the power rule. So in this case, 8 sits in front, x to the power of 7. We're going to do it term by term. This one, 5 times 12. 60 x to the power 4. Negative 4 times 4. Negative 16x cubed. Plus 10 times 3. That means positive 30x squared. Now this one, simply the derivative of kx is k, so this is negative 6. 5, the derivative of a constant is 0. So this gives us negative 6, this gives us 0, we don't write it. So the final answer is f prime of x is 8x to the power of 7 plus 60x to the power of 4 minus 16x cubed plus 30x squared minus 6. All right. And you may recall we did this with the definition, which took us some time, but now simply put f prime is 5. This is 0. In a split second, we have the answer. Now, this one, you have to put it in a format so that you can use the power rule. As you look at these exponential rules, and we're going to use the negative exponential rule, I can bring the x up and make it 2x to the power minus 1, ready for the power rule. So in this case, we can write f prime is 2 times negative 1 x to the power minus 1 minus, which makes this negative 2 x to the power minus 2, and that x to the power of negative 2, take it down, make it negative 2 over x squared. Again, using negative exponential rules, meaning if it's up, bring it down, make it positive. If it's down, bring it up, make it negative, and otherwise if you have to. So important to remember all of this. This one is 7 times 2, 14x. So very straightforward, everybody. What about this case? In order to differentiate this, first we are going to change square root of x to x to the power of 1/2. Then we're going to use a to the power of m times a to the power of n is a to the power of m plus n. So we used this one. We use this one. This has exponent 1. When we multiply these two, we get x to the power of 1 plus 1/2, or 3/2. This is 5x. Why are we doing that? So again, we make it ready for the power rule. Term by term. The first one, 3/2, x to the power of 3/2 minus 1, which is 1/2. 5x is 5. Negative 2, we don't write it because it's 0. And x to the power of 1/2, we know it's square root of x. We change it accordingly. The final answer is 3/2 square root of x plus 5. All right, d dx of a pi squared. What we should notice is that pi or pi squared or e or 1 or 2/3 or 1,000, they are all numbers. The derivative of any number is 0. Again, we have to use exponential rule to get each case ready for differentiation using the power rule. So this, we are going to use the negative exponential rule, bring it up, make it x to the power of -5. And according to the power rule, this would be -5 x to the power of -5 minus 1. This is -6. So f prime is -5 over x to the power of 6. We have to move this up to make it ready for the power rule of differentiation. So f prime is 2 over 7 times -3 x to the power of -3 minus 1. So obviously this is -4. So this is -6 over 7 x to the power of -4. Take it down, x to the power of +4. The final answer is f prime is -6 over 7 x to the power of 4. What about this one? Again, we can't use the power rule on that yet. So we have to rewrite it in the following manner. If you look at this part, it's x to the power of 5 minus 9. So x to the power of -4, therefore it's 2 over 9, x to the power minus 4. And now it's ready for the power rule, everybody. So now we are using the power rule on that, as we did in the previous examples. So what is f prime of x is 2 over 9 times -4 x to the power of -4 minus 1. 2 over 9 times the exponent -4 x to the power of the same exponent minus 1. So what do we get? This is -5. So we get -8 over 9 x to the power of -5. And x to the power of -5, according to the negative exponential rules, take it down, make it positive. So the final answer, f prime of x equals -8 over 9 x to the power of 5. So, in short, every question here uses the power rule. But to use the power rule, you have to do some sort of algebra. And as you can see, we have only one step of calculus. In every case, one step. Everything else is algebra. Okay? And that's the idea. You want to be careful. This is algebra, this algebra. Algebra, algebra, algebra. Algebra, algebra, algebra. So many steps of algebra, only one step of calculus. This one, we've already seen it again. Square root of x. We are looking at this one, everybody. So x to the power of 1/2. Now it's ready for the power rule. 1/2 x to the power of 1/2 minus 1. Again, this is the only calculus step. 1/2 minus 1 is negative 1/2. This one, you take it down, make it positive 1/2. So 1/2 squared of x, putting it back in the same format we received. Now, what about part B? This is the one we're going to use to rewrite this portion as x to the power of 4/5. So f of x is 2x to the power of 4/5. Now it's ready for the power rule. 2 times 4/5, x to the power of 4/5 minus 1. So one more time. 2 remains. 4/5 times 4/5, x to the power of 4/5 minus 1. So this is negative 1/5. So we get 8/5 x to the power of negative 1/5. This one goes down and takes a positive exponent. Positive 1/5, or the fifth root of x. The final answer is 8/5, the fifth root of x. For part C, later on we look at the product and the quotient rule, and sometimes students use a quotient rule by mistake. I say by mistake because you really don't have to. Why is that? Use your algebraic techniques first. This fraction is 10. This fraction is negative 7x. Now this gives you 0, this gives you negative 7, and you're done. You don't have to do anything further. Okay, so it's important to have a very strong background in algebra to be able to handle this stuff much faster. Okay. Find an equation of a tangent line to the graph of the function f of x equals x squared minus 3x minus 1 at x equals 4. So to find the equation of a tangent line, you need two things, everybody. You need the slope and you need the pair. To find the slope, you have to differentiate first. And now that we are equipped with the easy way out, we use the power rule and we differentiate. So f prime of x is 2x minus 3. If you plug in the 4 into the original function, you get the pair. Into the derivative function, you find the slope. So 4, you get 4 squared, which is 16, minus 3 times 4, which is 12. 16 minus 12 is 4, minus 1 is 3, so those are the pairs. If you plug into here, 4 times 2, 8 minus 3 is 5, so that's the slope. Y minus y1 equals m times x minus x of 1. That means y minus 3 must be 5 times x minus 4. Distribute the 5, you get 5x minus 20. Negative 3. Move it, make it positive 3. So y equals 5x minus 17 is the equation of a tangent line. Needless to say, if you plug in, the pair should work, and when it does, It just means that we did this right, doesn't say anything about the slope. Find the points for which the tangent lines are horizontal. Well, to get to the tangent lines and their slope, you have to differentiate first. So if f of x is x cubed minus 3x plus 3x squared plus 5, the derivative f prime is 3x squared minus 6x. But for him to be horizontal, we know horizontal lines have slopes that are 0, then you must set this equal to 0 and so on. And to solve this, first we factor out the 3x. We get 3x times x minus 2. 3x equal to 0, that means x equals 0, x minus 2 equal to 0, that means x equals 2. So those are 2 points, but put them as pairs so we understand. If you plug in 0, this goes to 0 and you get 5. So 0, 5. If you plug in 2, so 0. If you plug in 2, you get 2 cubed, which is 8, minus 3 times 2 squared, which is 4 times 3 is 12. 8 minus 12 plus 5 is equal to 1. And that's the second pair. So what points? The first one is 0, 5, and the second one is 2, 1. 2 different points. Exponential functions. Compute the derivative of the exponential function f of x equals a to the power of x using the definition of a derivative. We want to get to the fact that the derivative of e to the power of x is itself. So let's start with the general form a to the power of x. So using this formula, f prime is limit of f of x plus h minus f of x over h as h approaches 0. So replace the x with x plus h. That would be f of x plus h minus f of x, which is a to the power of x. So we get the limit of a to the power of x plus h minus a to the power of x over h as h approaches 0. Now, notice we can rewrite this as a to the power of x times a to the power of h, which means I can factor the common factor of a to the power of x for the top. This gives me a to the power of h. This gives me minus 1. And I write the limit of a to the power of x parentheses a to the power of h minus 1 over h as h approaches 0. Notice I'm going to put it next to this, and I'm going to take a to the power of x out, of course, because h is we are taking the limit with respect to h. A to the power of x is not a function of h. It can come out. So I'm going to write f prime is taking this out and this limit and putting it next to this. So f of x is a to the power of x. F prime is a to the power of x. The same thing times some quantity. This happened to be the limit as h approaches 0 of a to the power of h minus 1 over h. Now, next to each other, we see they are very similar. So what if there is a number such that this portion equals 1? So is there an a such that this limit of a to the power of h minus 1 over h as h approaches 0 equals 1? That's what we are looking for. And it's a trial and error, and you find it in the following manner. So this expression, a to the power of h minus 1 over h, you work on number 2, and you approach h. Only one side is good enough. You can go with both sides and get closer and closer to 0, like 0.1, 0.01, 0.001, 0.0001, and you plug it into this expression. So what happens? You get the following numbers. And if that's not good enough, you can pick one more like 0 point, and instead of 3 zeros, put 4 zeros and then 1. You see that according to this, the limit, so when a is 2, f prime of 0, the limit of 2 to the power of h minus 1 over h as h approaches 0 is 0.69. By the way, one might say, why f prime of 0? If you replace the x with 0, you get a to the power of 0, which is 1. Okay. Let's repeat that for number 3. And when we do that, we get the following numbers. And according to this, then let a be 3, f prime of 0 for 3. The limit of 3 to the power of h minus 1 over h as h approaches 0 seems to be 1.10. So we are looking for number 1. Did we find it? No. But for sure, 1 has to be somewhere in between these two numbers. In fact, this is closer to 3 than 2 because this gives you 0.69. That gives you 1.1. And as you know, this number is 2.71828, and it continues indefinitely. So this is by the trial and error. So here's the definition. E is the number such that the limit of, now we're going to change the a to e to the power of h minus 1 over h as h approaches 0 equals 1. So that's the definition of E. Also, I want to add the number E, known as Euler's number, was first discovered by mathematician Jacob Bernoulli in 1683 while studying compound interest, and popularized by Leonard Euler, who gave it the letter E as its symbol. Hence, it is called Euler's number. Now, we're going to continue with that thoughts. Geometrically, this means that of all possible exponential functions of the form y equals a to the power of x, the function f of x equals e to the power of x is the one whose tangent line at 0, 1 has a slope f prime of 0, that is exactly 1. What do we mean by that? I want to make sure we understand this as follows. If you look at, first of all, exponential functions where the base is larger than 1, you find e to the power of x to be between 2 to the power of x and 3 to the power of x. All of them have the same y-intercept at 0, 1. If you draw the tangent line at 0, 1 for some of them, you'll find some numbers. The only one that the slope is 1 is for y equals e to the power of x. Here's the reasoning. Where f of x is a to the power of x, we showed that f prime is a to the power of x times this limit of a to the power of h minus 1 over h as h approaches 0. If we replace the x with 0, everybody, let x be 0, we get f prime of 0. A to the power of 0 times the same expression. A to the power of 0 is 1. So therefore, f prime of 0 for f of x being a to the power of x is the limit of a to the power of h minus 1 over h as h approaches 0. Which means f prime is a to the power of x times this expression, which is f prime of 0. Therefore, one way to look at f prime of x is f prime of 0 times a to the power of x. So we write the same thing for e to the power of x. So if f of x is e to the power of x, f prime of x is f prime of 0 e to the power of x. Because we've shown that it's e to the power of x, then f prime of 0 must be 1. So E has this definition, as you recall from compound interest, the limit of 1 plus 1 over n to the power of n as n approaches infinity, or the limit of 1 plus h to the power of 1 over h as h approaches 0. And we know it's a number. It's not a missing number. It's 2.71828, and it continues indefinitely. And now we also have the following. E is the number such that the limit of e to the power of h minus 1 over h as h approaches 0 must be 1. However, all we need to know really, if f of x is the power of x, so is f prime of x. That's all we need to know. I just wanted to go over this concept so with a little bit more details in essence. All right, we want to differentiate f prime. We want to find f prime and f double prime, where f of x is e to the power of x minus x, reminding you of the formulas we've discussed. So if I want to differentiate this, I'm going to do it piece by piece. F prime of x is e to the power of x, gives me e to the power of x minus x, gives me minus 1, and I'm done. What about f double prime? Well, higher order derivatives of f of x. The derivative of a function y equals f of x is itself a function y prime equals f prime of x. Therefore, you can take the derivative of f prime of x referred to as the second derivative of f of x, f double prime, or f superscript in a parentheses x. This is not f to the power, this is not f squared, okay? This is not the exponent. It's put in a parentheses, okay? This differentiation process can be obtained to find the third, fourth, and successive derivatives of f of x, known as higher order derivatives of f of x. Because prime notation becomes cumbersome for higher orders. Think about it, f prime, f double prime, f triple prime, and eventually when do you stop? We use the superscript notation, f and the superscript n in a parentheses of x to denote the nth derivative of f of x. So in this case, f double prime is easy, or just f superscript 2 inside the parentheses. That means differentiated again. So if I differentiate e to the power of x, I get e to the power of x minus 1 gives me 0. So simply e to the power of x, and I'm done. What about y equals sine t plus pi cosine t? We are going to differentiate piece by piece. Sine, the derivative is cosine. We get y prime equals cosine t. Plus pi times cosine t. The derivative of cosine is negative sine. So plus pi times negative sine t, which becomes minus pi sine t. H of t is the fourth root of t minus 4 e to the power of t minus cosine t over 2. We want to differentiate that. To make sure it's doable, we are going to change this to t to the power of 1/4 to get this ready for the power rule. This one you don't have to change, but I like to rewrite it as negative 1/2 cosine t. So I want everybody to see that this is just a number. You're differentiating cosine t in essence and times negative 1/2. So starting with that, we get 1/4, t to the power of 1/4 minus 1. This one is itself, just write it, because it's an exponential e to the power of t. This one is negative 1/2 times cosine is negative sine, so negative 1/2 times negative sine t. One-fourth minus 1, negative 3/4. This you take it down. 1/4, t to the power of positive 3/4, which is the fourth root of t cubed. This one is itself, negative times negative is positive. So the final answer, 1/4, fourth root of t cubed, minus 4 e to the power of t, plus, I'm going to write it in the same format, sine t over 2, or you can say plus 1/2 sine t. The distance in meters of an object from a starting point is given by S of t equals 2t squared minus 5t plus 40, where t is time in seconds. What is the velocity of the object from 2 to 4 seconds? I hope you remember we did this. In fact, it was even in the exam one review. So the average velocity is the total distance over total time. So S of t sub 2, that means S of 4, minus S of t sub 1, that means S of 2 over 4 minus 2. Obviously, the denominator is 2. What is the numerator? Let's plug in. 2 times 4 squared minus 5 times 4 plus 40. Then you plug in 2. 2 times 2 squared minus 5 times 2 plus 40. We have done this already, okay? This is 16, 32 minus 20 plus 40. They add up to 52. This is 4 times 2 is 8 minus 10 plus 40. They add up to 38. So we have 52 minus 38, which is 14 divided by 2, 7 meters per second units of the numerator over the units of the denominator. We had seen this before. Now, what is the instantaneous velocity and acceleration of the object? What is the velocity and acceleration of the object after 6 seconds? So velocity, when one point in time is given, is really the instantaneous velocity, which is the derivative. So v instantaneous is s prime of t. So differentiate this and you get 4t minus 5. So 4t, 2t squared becomes 4t minus 5. And now, after 6 seconds, 4 times 6, 24 minus 5, 19 meters per second. What about the acceleration? Acceleration, by definition, is the second derivative of the position function. A of t is b prime or s double prime. That means differentiate this again. Now, notice if we differentiate this again, we get 4, just a constant, which means it's always 4, and it doesn't matter after 6 seconds, 2 seconds, or 10 seconds. What are the units? Meters per square second. I want to discuss the units and why it is meters per square second. So this is ds dt, which refers to change in distance over change in time with the units of meters per second. A of t is a dv dt. Units of the velocity, meters per second. Units of time, seconds. And you get meters per square second. That's how you arrive at the answer. When does the object reach a velocity of 31 meters per second? You said the velocity equals to 31 meters per second. And to solve this, we move the negative 5 becomes positive 5. With 31 is 36 divided by 4, 9 seconds. So when does the object reach the velocity of 31 meters per second? At t equals 9 seconds.